Hello everyone. Today we are going to talk about error propagation. And the error propagation is really that, let's say, let me get to a little bit smaller tip here. Okay, so let's say you have a pipe, right? And that pipe has a flow rate of Q, okay? And let's say it fills a sort of a pool, right? So it's a pool. And then you are trying to measure the time required to fill that pool, right? So then that means that you have a flow rate measurement that you've done, right? And you are going to estimate the amount of time that's going to fill the pool. However, that there is some uncertainty, right, associated with this flow rate measurement, right, that will actually, let's say, plus minus u time, right? That's going to propagate into your measurement of time because you are only, doing it that way. So the other thing that probably is important is that you have a volume associated with this, right? And then that also has some uncertainty of that volume measurement, right? So then the time that you need, right, for your answer will have a uncertainty that is coming from both the volume measurement and the flow rate measurement, right? That this example can be sort of expanded, obviously, but then the idea here is that quite often we need to know how error in one instrument, right, propagates into the instrument, it propagates in the measurement that we are doing, right? In other words, if we have a measurement or a quantification that we are doing, right, based on a measurement from a system. Let's say, let's do XY graph. So this is our input, right, from our sensor. Okay, and let's call that X, and then we have calculated value. Right, let's call this Y. Okay, so then the question is, if they are linear or nonlinear, depending on what it is, right? For any given value of X bar, right, because that's the sample mean that we have measured, right, that's going to amount to a measurement of Y bar. The question that we are interested today, right, is if we have a uncertainty of X bar plus minus, right, Ux, and X bar plus minus, right, Ux on the other side, how that error then propagates into Y. In this case, that will be Y bar minus Uy, and that will be the Y bar plus Uy, right? So then the question is then how Uy is defined in sort of the terms of Ux. Okay, let me redraw this here so we will better understand it. So here's my input-output relationship. Although this is input-output, meaning here is that the input here is X bar is my measured value, right, from my sensor. And I also have the uncertainty associated with it, with Ux, so that will be X bar plus Ux, and then that's going to be X bar minus Ux, okay? And that corresponds to a Y bar value, okay? So what we are really after here, right, is how the change or uncertainty in Ux translates into Uy, which is shown here by Y bar minus Uy, and then the Y bar plus Uy, okay? So what we are really trying to say, and this graph is defined by a function of X, right, and that's Y, right, y bar. And then what we are really trying to understand is that how we can define or estimate y bar plus minus uy, right, which is then a function of, right, x bar plus minus ux. Okay, so if you remember, you can estimate a function at a point, right, using Taylor series expansion, right, which states that that a function fx, right, at point C, right, can be approximated as, okay, so the fx can be approximated as fc, right, plus the first derivative of f at point C, right, divided by 1 factorial times x minus c, okay, plus, just going to write it below here, second derivative of f at point C divided by 2 factorial, right, times x minus c squared, and then it can go up to, you know, n. Usually you use the first order, right, depending on your application. Usually the first order used, second and third orders usually are much smaller, but it depends, you know, to your application. Okay, let's then try to say how can we estimate y bar plus minus uy, right, which is actually defined as f x bar plus minus ux. Okay, so basically what I'm going to do here is that whenever I see fx, in this example, I'm going to replace it by x bar plus minus ux, and that should give me the estimation of the error in ui. Okay, so then the Taylor series expansion of that will be, and I will of course do this at x bar, right? So that's at x equal x bar. Okay, so then let's do that approximation. So that will be f x bar, okay, plus the first derivative of fx, right, bar dx at x equal x bar, okay, then that will be x bar plus minus ux minus x bar. Okay, I can write the second term here if you want to, so that will be 2 factorial, right? That will be d squared fx dx x equal x bar times x bar plus minus ux minus x bar squared, and so on and so forth. For the purposes of our application, we are also going to assume that this is small enough, so that goes to 0, so we're going to ignore the second order term, okay? And then, so here's the x bar, here's the x bar, so they cancel each other out, okay? And then, if I were to write it down, right, then the approximation of y bar, right, plus minus uy, right, can be written as fx bar, yeah, plus delta fx bar delta x, there's bar here, times x, it's at x equal x bar, right, times ux. Since we know that the y bar was defined by fx bar, okay, that means that the ui is delta, right, y bar dx times ux. Okay, so basically this is the uncertainty estimation of y based on the approximation on the approximated value of uy, right, based on the ux, okay, that has been propagated. If your y bar, okay, is a function of different measurements, so let's say x1, x2, x3, right? From our initial example, maybe you can think of that's the flow rate and the volume. Let's do 2 then. Okay, x1 and x2 bar. Then your uncertainty of y, right, is going to be dy, right, the x1 times ux1, okay, plus dy divided by the x2 times ux2, okay, and obviously we have to use RSS to combine uncertainty, so that would be square, and that will be square root, okay. So if you have multiple inputs to calculate a outcome, right, which is say the y bar, then you're going to have a number of uncertainties that will sort of contribute to that. Okay, so let's do an example. I always like to do it in examples so that that makes it much easier. Okay, so let's do example. Okay, let's say we want to measure the area of a plate using a caliper. Okay, so I look at the spec sheet of the caliper. Okay, I found that the resolution, right, is plus minus 0.01 millimeter, and that's at 95 percentile. Accuracy, right, is plus minus 0.02 millimeters at 95 percentile. Okay, and repeatability, okay, is given as plus minus 0.01 millimeters at 95 percentile. Okay, when I measure the plate, okay, so here's a plate that we have measured. Okay, the height was 5 millimeters, right, and then the width was 10 millimeters. Okay, so then the area of the plate, okay, is a function of two measurements. One is width, right, and then the other one is height. Okay, and it's given as the width times height, right, and then the uncertainty will be, what we're trying to find is that the UA, right, at 95 percentile. So the question is, what is UA? Okay, so since we have two measured variables, okay, based on the definition we just gave you, UA, right, is going to be combination of the errors in width and errors in height, which will be then defined as derivative of A, right, respect to width times the uncertainty in width squared plus derivative of area with respect to height, okay, and then the uncertainty in height times that squared and square root. Okay, so we basically need to now figure out what is the uncertainty of width, and that's one uncertainty of height, and we are just going to plug that in to our equation. Okay, keep going. So for our case, in this case, uncertainty in width is equal to uncertainty in h because you use the same caliper, right? Same caliper. In that sense, we can define that as the combination of, right, again, zero order uncertainty, right, which comes from the resolution, and the instrument uncertainty that comes from the spec sheet. U0 is basically half of your resolution, which was given as 0.01 millimeters, so that will be 1.2 times 0.01 millimeters, right? And that's defined as plus minus 0.005 millimeters at 95 percentile. Okay, so then my UC, right, in the instrument error is the combination of the accuracy and repeatability, right? To do that, I'll just basically do RSS again, so that will be 0.02 squared plus 0.01 squared in square root, and that's going to get me plus minus 0.00224 millimeters at 95 percentile. Okay, so then UW equal to UH is going to be the combination of my U0 and UC. Okay, in that case, it's going to be square root of 0.005 square, right? That's U0 plus 0.00224 square, that's UC, in square root, and that answer will be plus minus 0.023 millimeters, and that's at 95 percentile. Okay, let's remember how we did the uncertainty for the area, right? Uncertainty for an area was given as in RSS format, UA dW, right, times UW squared plus dA EH times UH square in square root. Okay, so let's take and remember here that the area was given as width times h. Okay, so let's take the derivative of a, right, respect to w, right? That's going to be h, and then derivative of a with respect to h will be w, right? So then I can write my UA as h times w squared plus w times UH square in square root. Okay, if I put everything together now, I will see that that's going to be width was 5, right, and my sorry, the height was 5, and then the width was 10, right, millimeters. Okay, and if I put everything together now, that's going to look like 5 times 0.023 square times plus 10 times 0.023, right, square root, and that gives me plus minus 0.256 millimeters. That means that my A area, right, plus minus the UA is going to be 50, right? 50 plus minus 0 0.0, sorry, 0.256 millimeters at 95 percentile. Of course, it's 95 percentile too. Okay, so that's pretty simple example, right? Let's go and do one more. So this time, instead of using a caliper, let's say we used a ruler. Okay, let's draw a ruler here, right? That's a bunch of numbers here. And then the resolution of the ruler was, right, plus minus 0.1 centimeters at 95 percentile. And let's say that's the only thing that we have, okay? So then we get a cylinder, okay? And we measure the cylinder's height, h bar, and then the diameter d bar, right? And what we want to know is that what is the uncertainty in the volume measurement, okay? Let's say we measured d bar as 2 centimeters, and then the h bar as 10 centimeters, okay? So the question here is that the volume, right, is a function of the diameter and height, okay? And the question here is that if you were to calculate V bar, right, what is the uncertainty of UV? So the question is, what is the uncertainty of that volume? Okay, so let's go ahead and start that example. The volume is defined as pi over 4 d square h, right? So that means that that's two variables, right? That means that my UV, right, which is the uncertainty, is going to be, again, I'm going to do delta V delta D times UD square plus delta V delta H times UH square root, okay? So I know what is the UD is again equal to UH, right? Because I'm using the same ruler, and that's equal to, again, square root of U0 square plus UC square. Since we don't have a spec sheet associated with this ruler, our UC is 0, right? So that means that it's only the U0 squared with square root, right? And then our U0 is half of our resolution. So that will be 1.2 times 0.01, or I'm sorry, 0.1 centimeters. And that's going to be plus minus 0.05 centimeters at 95 percentile. Okay? So then we can write the our definition for the uncertainty of V, right? That's going to be okay, the derivative of volume respect to D, right, will be pi over 2 dH times UD square, right, plus pi over 4 d square UH, okay? So that's the derivative of V respect to, that's the derivative of V respect to D, and that's the derivative of V in respect to H. Okay, it's the H, okay? So if I were to put this in and figure out what that will be, right? That's going to be, that will be pi over 2 times 2 times 10 times 0.05 squared, right, plus pi over 4 times 2 times 0.05 square root, right? And if I do that, that's going to be 1.6. Okay, so then what we can do is to write the volume, right, estimated value, volume plus minus a uncertainty, right, is going to be 31.4 plus minus 1.6, okay, and that was in centimeters, so that will be centimeter cubed at 95 percentile. Okay, let's do one final example, and this time let's increase the complexity a little bit, but it's still going to be a pretty straightforward example. Okay, so let's say we have a device that we measure power. Okay, measured power. Okay, this could be engine or whatever, right? And to do that, we used a resistor, right, and a multimeter. Okay, let's look at the multimeter specs. Multimeter specs says that we have a resolution of plus minus 0.1 amps, 95 percentile. We have a linearity. Okay, that's plus minus 0.05 amps at 95 percentile. And we have a hysteresis. That's going to be plus minus 0.04 amps at 95 percentile. Okay, and that's basically reads the current, right? And then let's look at the resistor, right, which is going to read resistance in ohms, right? Resolution, right, is plus minus 0.1 ohms, and precision is plus minus 0.1% of output. Okay, and our readings were given as current, sort of the sample mean of current was 3 amps, and then the resistance mean was 10 ohms. Okay, so then the question is the power, right, which is the function, which is a function of I and R, is defined as I bar squared times R, and that's 90 watts, right, based on measurements. And the question is, what is, right, the UP, the uncertainty in that power that is propagated from the measurements of current and resistance. Okay, UP is then defined as, right, let's write the definition here since we have only two variables, right? That will be delta P, delta I times UI squared plus delta P, delta R times UR squared. Okay, so let's start with the uncertainty of our multimeter and go from there. So the uncertainty of the multimeter, right, is defined as square root of U0 square, UC square, okay, and that's only half of the resolution, which is 1.2 times 0.1. It's going to be 0.05 amps. This is going to be defined as the combination of linearity and hysteresis, right? In that case, it's going to be 0.05 square plus 0.04 square root, right? And that's going to get me plus minus, so we also have plus minus here, 0.064 amps. Okay. Now, if you were to combine these two, right, that's going to be square root of 0.05 square plus 0.064 square in square root, and that's going to get me plus minus 0.051. I'm sorry. That's going to get me 0.051 amps, right? And that's at 95 percentile. Okay, so if I look at the resistor, right, what is it? It's going to be again the U0 square plus UC square, right? And that's going to be 1/2 times 0.1, and that's going to be 0.05 ohms, right? Again, that's going to be plus minus. Then this is going to be 1% of the output, right? Remember that the R measured value was 10 ohms, right? So that means that it's going to be 10 ohms, and that's going to be 0.1% of that, so that will be 0.001. That's going to give me 0.01 ohms. Okay, so let's put them together. That's going to be 0.05 square plus 0.01 square in square root, and that's going to be plus minus 0.051 ohms at 95 percentile. Okay, so we have everything we need. We have the uncertainty of the multimeter, uncertainty of the resistor, right? And let's put it all together, right, in our sort of final thing. So remember that the uncertainty of power, right, was defined as dP di times ui square, square goes other place. Ui times square plus dP dr times ur square, right? And all of that goes into square root. Okay, so this term is becoming 2ir ui, right, square, and this term is becoming I square ur squared, right? Just take the derivative of power with respect to I or R, and if I put everything together, then UP, right, is going to be 2 times 10 times 3 times 0.081 square plus 3 square times 0.051 square root, and that's going to give me plus minus 4.9 watts, right? That's at 95 percentile, and therefore my power measurement, right, plus minus the uncertainty in power based on the measurements in resistor and multimeter, right, is going to be 90, okay, plus minus 4.9 watts. That's 95 percentile. And basically, that's how you propagate your error from multiple sensors into one measurement. In your second experiment, right, in your first experiment with accelerometers, you are not going to do the this, but in your second experiment, right, in order to calculate the heat transfer, you're going to have to rely on your temperature and area measurements, and you're going to have to be combining those two. So if you have any questions, please let me know, and I will be able to answer them. Thanks.